In this video, we'll be discussing the exponential function for complex numbers. As with other things in complex numbers, we often have to redefine certain functions that we think we know in real numbers to fit our complex numbers purpose. So first, let's start with a definition, and this is indeed a definition, we don't need to prove it. So e to the power of any complex number z is given by e to the x, and then in parentheses we'll put cosine of y plus I times sine of y. And x and y are the real and imaginary parts of z. So z equals x plus iy. So if we want to plot it, this will be x, and then this will be iy, and then x plus iy or z will lie right there, for example. And keep in mind, x and y are real numbers. So it's the real and imaginary part. And e to the z is given just by this expression right here. So now we'll look at some properties of the exponential function. So if x plus iy is one complex number, z, and s plus it is another complex number, w for example, then this is e to the z plus w, and just like in real numbers, this is equivalent to e to the z times e to the w. Okay, and the way to prove this, if you wanted to, would be you would write down this expression, and you would write down the expression for both of these, add them up, and then kind of factor out terms until you get to this expression. So it shouldn't take that much work. Now let's look at something more important. We want to find the modulus of e to the z. Now this will require us to draw a little graph. So let's draw a graph, and let's draw a point right here. And let's suppose that the distance from the origin to that point is e to the x. And that is a real number because x is a real number. And let's say that the angle from the origin, from the real line to this line segment is y, and this y is given by the same as this y over here. So now, what is the x component right here? Well, just using trigonometry, we know that it's going to be e to the x times cosine of y. And what is the y segment here going to be? Using trigonometry again, we know it's going to be e to the x times sine of y, and it has to be times I because we're dealing with the imaginary axis here. So now, what is that point in the terms of what we just found? Well, it's going to be e to the x cosine y plus I e to the x sine y. And if we factor out the e to the x, we get that it's e to the x cosine y plus I sine y. And the thing to note is that this is the exact same as what we wrote up here. So this is equal to e to the z. So we found that this point right here is e to the z, and we want to find the modulus of e to the z, and we found that it's given by e to the x, because that's the distance from that point to the origin. So that is a good thing to keep in mind also. The next thing to keep in mind is right here. E to the z can never be what? It can never be 0. And to convince ourselves of this, let's see. If e to the z were to be 0, then one of these components would be 0. Either e to the x is 0, or cosine y plus I sine y is equal to 0. Is e to the x ever 0? Well, we know from real numbers that that's not true, because if we draw a little graph of e to the x, it looks like this, remember? And it goes really close to 0 as it approaches on the left, but never touches 0. So this can indeed never be 0. Can this part ever be 0? Well, if this part was 0, then cosine y would have to be 0, and sine y would have to be 0 at the same time. And we know that there's no possible y you can plug in for that to be true. So this can never be 0, and this can never be 0, which means e to the z can never be 0. So the origin is excluded. You can never map to the origin using this function right here. So now let's see what to do. Now let's say we want to solve w equals e to the z, where w is some complex number. Well, let's kind of start breaking it down. W is a complex number, so it lies somewhere on the complex plane. Let's put it here. And we know that it has an angle, so theta, and we'll measure it from the positive real axis. And we know that it has a magnitude here, which we'll call r. So this is the modulus of w. The distance from w to the origin is r, and this is theta. So what is this x distance right here? Well, using the calculation kind of type we had up here, we know that this x distance right here will be r times the cosine of theta, and this right here will be r times the sine of theta times I, because we're dealing with imaginary axis right here. So that means w, all in all, equals r cosine theta plus ir sine theta. And theta might make this expression negative because we're taking a negative theta. It will make it negative. So then this will equal r times cosine theta plus I sine theta. So this is a little bit nicer for us to work with because of what e to the z is defined as up here. So let's write that right now. W we found was r times cosine theta plus I sine theta. And the definition of e to the z says it's e to the x times cosine of y plus I sine of y. So this parallel kind of definition will help us a lot. And it's going to help us a lot because now we know that r has to equal e to the x. So that means, I'll write it here, r equals e to the x, and now we want to solve for x, which means that x equals natural log of r. That much is certain. X equals ln r. Now also, theta could equal y, right? That will solve this for sure. Theta equals y. But what else could y equal? Y could equal theta plus 2 pi, because that will also solve this, because cosine of theta plus 2 pi is the same thing as cosine theta. Sine of theta plus 2 pi is the same as sine of theta. And really, it's not just 2 pi, it's any multiple of 2 pi. You can have n be any integer, positive or negative. So this has infinite solutions. The solutions are of the form. So x is ln r, and y is any of these. And any of those z's, where you have z equals x plus I times this y, will solve this equation. So we see that unlike in real numbers, this equation actually has infinite solutions, which is something interesting to note. So let's do one last thing in this video, will be mapping. So this is our function, f of z equals e to the z. And we want to map it from our z plane here to our f of z plane here. In previous videos, we did it all in one plane, but it'll be a little bit cleaner if we do it this way. So let's actually just map a strip. So how big of a strip? Well, we can arbitrarily just start at any y value you want. Let's start at y naught. And the width of this strip is going to be y naught plus 2 pi I. Okay, so then the width of this strip is 2 pi I because it's y naught to y naught plus 2 pi I. And then this strip just goes infinitely in both directions. In this direction and in the leftward direction, it goes infinitely. Now, mapping means that we're going to take every single point inside this strip and we're going to see where it lands us in this f of z plane. So what's the f of z associated with every single point inside the strip? Seems like a very big task, but if we find the patterns, it'll go really quickly. So let's just go one thing at a time. So let's say we want to map a line in this strip. Let's just say we want to map this green line, see what happens to it. Well, let's write e to the z as we know it. So it's going to be e to the x times cosine y plus I sine y. And this green strip is given by what? Well, the x is always changing. It's going from negative infinity to positive infinity. So it's going to be x, changing x, but the y is set. It's just some y that we pick. So let's say, call it y1. So it's going to be x plus I y1. So then e to the z is going to be e to the x, which is changing, times cosine of y1 plus I sine of y1. And remember what we said. The y1 represents the angle. So where do we do that on the back? Here. We said that the y is representing the angle. So then on the f of z plane, we're going to have angle y. And what is the radius given by? Well, it's given by e to the x. So this length is e to the x. And this radius we said is always changing. So it starts at, this can never be 0, but it starts very close to 0 and just expands outward. So what this green line maps to is a ray, an infinite ray that starts very close to 0 and goes all the way out in the infinite direction. Now, what if we take a new green ray, a little bit higher? What have we changed? Well, x is still going from negative infinity to positive infinity, but we've changed y1 to something a little bit greater than y1. So maybe this angle is a little bit greater now, but that still doesn't change that the ray goes on to infinity. And we do like this. We just take all these rays. We can just take infinite amount of rays. And keep in mind that this y, it goes from y naught to y naught plus 2 pi I. So that means the angle is changing it's changing by 2 pi. So really we're starting somewhere. Let's just say let's say y naught was over here, and then we're changing by 2 pi. So we're going one full rotation around. And this top purple line I drew, really I think I should have drawn it dashed, because we don't have to approach it, but we could. It'll just be overlap. So we're going all the way around until we approach this ray. And in the process, we're drawing every single ray possible. And when you draw every single ray, what do you really draw? You're drawing the entire complex plane. But it's important to note, except the origin, because we noted on the back of this paper that e to the z is never 0, the origin. So we have just drawn the entire complex plane. So what to take away from this is that a strip of width 2 pi I will map to the entire complex plane, except the origin.